everybody. Today we're going to hit on a topic a lot of you have some experience with from the past called the scientific method. I'm going to open that up a little bit more and call it the scientific process. The reason I'm going to do that is because, every teacher has their own way of explaining the scientific method, and every teacher also reports a different number of steps that scientific method takes up. The scientific process then would just kind of be a generalized term to describe the actions that take place during any scientific endeavor. We can't even forget about scientists sometimes just, guessing and checking and moving things around just in order to get a ballpark of where they should be experimenting at some particular level. But to report anything as truly scientific, evidence must be shown that the scientific method was processed, and they went through a series of steps in order to reach their conclusion. So let's think of an example here of, let's say it's a warm summer night, some storms hit, the power goes out. So you rush to find a flashlight. You go to your go-to spot in the house and you find your flashlight, and you go ahead and you flick the switch and nothing. You're still in the dark. So your first thought is batteries are dead. So you're going to go ahead and you're going to swap out the batteries if you have some new ones laying around. So I'm going to take these out here, put in a new couple of batteries, and we'll see if that fixed our problem and we can get some light here in the dark. So we go ahead and we give it a shot and nothing. So you went ahead and you tried to solve your problem and you failed. So your next step is either saying my flashlight's broken or take the next step. Let's say that you just happen to have an extra bulb laying around. So your next step then would to be go and check the bulb. Maybe just the bulb needs replacing and the batteries are fine. So what we're going to do is we're going to swap out the bulb. So I'll catch up with you in a minute after I swap out the bulb in my flashlight. So I've gone ahead and I've swapped out the bulb in my flashlight. I'm going to go ahead and give it a try, and I have light. So what's the big deal? I just figured out a small problem. Well, I actually used the scientific method in order to do so. Now, I didn't think to myself, I'm going to use the scientific method and figure out what's wrong with my flashlight. My brain just kind of did it. I know how to solve problems, but I can definitely relate finding what's wrong with this flashlight 2 steps in the scientific method. For example, one of the first steps is observations. I observed that my flashlight wasn't working. And I came up with a question after that. I said, okay, why is my flashlight not working? I went ahead and informally suggested a hypothesis to myself, such as, if the flashlight isn't working, it must be dead batteries. So I then conducted an experiment. I swapped out my batteries, and I took data by flicking the flashlight on. When I did, the flashlight did not turn on. So the data, after I analyzed the fact that it didn't turn on, suggested that my hypothesis was being rejected. It was not being supported in any way. So what I did then, it wasn't a total failure because I just re-hypothesized. I said if the batteries aren't bad, well then it must be a bad bulb. So I went ahead, I did another experiment, I swapped out the bulb for a new one. I went ahead and turned it on. Sure enough, I got light. So the data said, yes, the light turned on. I analyzed it, and then I went ahead with a conclusion. I said, well, my hypothesis was supported in the fact that it was a bad bulb. So, of course, no one does that. But as you can see, the steps of the scientific method were there as I solved the problem of my flashlight not working. So what we can say then is science is ultimately based on observations. That always gets the scientific method and scientific process going. You observe something called a qualitative or even sometimes a quantitative observations. Qualitative are observations that you do through your 5 senses. Mine was through sight for my flashlight. Quantitative is more dealing with numbers. Either one can be used to base your scientific endeavor, your scientific experiment off of. What are some examples of qualitative observations that might need some investigation? Well, as I walk around the house and I look at my garden, I notice that the plants in the house, we'll talk about those first, they seem to bend towards the window. If I look at all my plants, they're kind of leaning towards the window. So the question I have is, why do my plants lean towards the window? I noticed the same thing happening in the garden. The garden plants kind of lean towards the sunlight as the day goes on. And as the day shifts and the sun moves places, the plants kind of bend towards the sun. Why do the plants do that? So I've just knocked out my observations qualitatively through my eyes, and that led to a question. Why do they do that? So that is the beginning of any scientific endeavor that you wish to undertake. You're going to observe something, and then you're going to ask a question about it. The next thing you're going to do is you're going to come up with a testable prediction called a hypothesis. Now, a lot of you guys learned in the past it was called an educated guess. But you got to be careful with an educated guess, because someone might be educated in all the wrong things and make a guess that kind of sounds silly sometimes. Like, for example, if I said, what's at the end of a rainbow is my question, and I hypothesized that there was a pot of gold there. That is kind of a silly hypothesis because I was educated in the wrong thing. Someone once told me at the end of both sides of a rainbow, you'll find a pot of gold. And we know, of course, that's kind of ridiculous. But a testable prediction, if we use that as the definition for hypothesis, can be shown to be true or false by experimentation or observation. So let's go ahead and we'll take a look at some hypotheses and we'll determine whether they are of quality or not. For example, and let's go ahead and we'll pit two hypotheses against each other. For example, if we look at number one on both sides, the first on the left side says plants will grow better when given Miracle Grow. On the right, plants will grow taller when given Miracle Grow. Okay, so which one is better? Which one is a better hypothesis for an upcoming experiment? Well, I hope you went ahead and you picked the one on the right, because we all know what taller means. There's no other opinions on what taller can mean. But what about the word better? Better is kind of subjective. Some people might think greener, some people might think bushier, some people taller, some people fatter. We don't know. So by using a weak word inside your hypothesis, it weakens the whole idea of your hypothesis. So we want to be very precise and use terminology that fits the description of what exactly we're trying to get to the bottom of. Number two, left side, girls are smarter than boys. Right side, girls will score higher on math tests than boys. Well, smarter on the left is another one of those subjective terms. Smarter in what? Okay? On the right, girls will score higher on math tests than boys. That's very, very specific, as a hypothesis should be. Let's take a look. Could both of these be tested? Because that's another key thing. If it's a testable prediction, experimentation should be able to get us an answer. So with example number one, the plants in the Miracle Grow, could we experiment with that? Of course we could. We could give plants Miracle Grow and see if they grow taller. Number two, could we test girls and see if they score higher than boys on a math test? Absolutely. We could take a math test right now and find the answer to that. Number three, hermit crabs like colorful shells. Nice. And number three on the right, hermit crabs choose colorful shells over drab shells. Now, this one takes a little bit more thinking because we have to look at the terms and decide which one is a better fit for science. So those that think the three on the left is better, I gotta point your attention towards the word like. It's very difficult to know what a hermit crab likes. As far as I know, there's no such thing as a hermit crab psychologist, so it'd be very difficult to figure out what it actually likes or not. However, the three on the right, hermit crabs choose colorful shells over drab shells. Could we go ahead and test for that? And the answer is yes. We could give hermit crabs a choice. Give them an area to choose colorful shells over ones that are drab and see what they do. So in each one of these, we can definitely find a better and a worse example. And it just happens that all three, whoops, we should flip that around for a second. Let's go ahead and do that now. So the better ones are on the right and the worse ones are on the left. That makes a lot more sense. All right. Just had to check and see if you were watching too. All right, so back to this. One more thing I want to say with it is the fact that not only do some hypotheses rank as better or worse. But we also then will take our hypotheses and do something to them called an if-then format. An if-then format kind of sets up the appropriate, I guess we could say, direction of your statement. And we kind of always begin our hypotheses with the if, and then somewhere in the middle we find the then. So taking a look at better example with the Miracle-Gro, this one over here, if I had to translate that into an if-then type statement or prediction, I could say if plants were given Miracle-Gro, then they will grow taller. So an if-then makes up part of the prediction portion of your hypothesis statement. I could do the same thing with number 2, with the girls versus the boys on the math test. If girls and boys are given math tests, then the girls will score higher. So again, if-then format is allowable there, and of course appropriate. And then the last one here, this one's a little bit tougher. Hermit crabs choose colorful shells over drab shells. Sometimes you can throw an if-then statement in there straight up and it works out real nice, and other times you gotta kind of work around the words. So for this one might come up with a statement like, if given a choice of colorful shells versus drab shells, then hermit crabs will choose colorful shells. So I had to kind of monkey around with the words a little bit, move them around, add some, and that's allowable too in order to come up with an appropriate style of hypothesis. After you come up with a appropriate and viable hypothesis, we're then going to go ahead and test that. And we're going to do that using, of course, an experiment. An experiment is a carefully planned procedure designed to test the hypothesis. That's the purpose. Usually it's numerical in nature, number of steps, and you want those steps to be concise statements. You want them to be simple enough but detailed enough where someone else could go ahead and do your experiment with little trouble and come up with results just like you did. Now, 2 parts will make up your groups within your experiment. The first is called the experimental group. And this is the group, the number of individuals or the number of research subjects that receive some kind of treatment or condition. So it's what you're doing to a special group that you want to find answers to. But we also have another group. It's called a control group. And you don't do anything to this group. In fact, you do exactly the same as condition-wise what you do with your experimental group, but you don't give them the treatment or the condition. So if it was plants, for example, you're going to go ahead and you're going to water them the same, as long as water is not a variable. Give them the same amount of sunlight, give them the same amount of atmospheric conditions. Otherwise, you can't really compare one versus another. Because if I go ahead and I do a plant growth experiment, and one of my plants that I'm giving my, say, Miracle-Gro treatment to sits in a window, and the other one is beside the window and there's a wall of bricks in front of it, well, can I be sure that it's the Miracle-Gro that's really allowing my plants to grow? Or is the fact that it's in front of a window? I don't really know unless the control is getting the exact same conditions except for the ones that we're testing. Let's take a look at our Miracle-Gro example a little bit closer. Our hypothesis is plants will grow taller when given Miracle-Gro. Our prediction is if plants are given Miracle-Gro, then they will grow taller. Alright, so what are we going to do? We're going to test that hypothesis. And we're going to say plants of type A and B are both given the same amount of light, water, and stored at the same temperature. The only difference, though, is that plant A is given the Miracle-Gro. So all the plants of this type are given that. These are not, they're just going to be existing at the same environmental conditions as this group here. So all control variables are kept constant except the ones you are testing. What kind of control variables? Well, we said in the statement, light, water, and temp. Those 3 things. Okay, all the same for both. Next, let's identify a couple of other variables that are involved with your experiment. First, independent variables are changes that occur in an experiment that are directly caused by the experimenter. In our example, it's the Miracle-Gro addition. So our independent variable then is the addition of Miracle-Gro to plant type A. Dependent variables are changes that occur due to the independent variables. So, what are we looking for? What was our hypothesis all about? Well, it was about that plants would grow taller when given Miracle-Gro. So, what depends on the Miracle-Gro? The height of the plant at the end of our experiment. So, what we're looking here is how tall do these plants get? That is our dependent variable that's in our experiment. During our experiment, of course, we take data. And data is usually thrown into some kind of organized chart. As we can see here, this is a very nice data table, very simple. Here is the date of data collection. And you can see that every 3 days, it seems like data is being collected. And here, it leaves a little bit of information out that would be nice, like what unit they're measuring in. Is it inches or centimeters? And is it an average? That could be put into the headings for each of the columns here. But we'll imagine that it's centimeters. So plant A, on average, they were 10 centimeters. Plant B, 7. Plant A, 3 days later, was averaging 25 centimeters. Plant B is at 15. 45 versus 20, 60 versus 35. So 12 days later, your plant A's are averaging 68, which is way up here, and your plant B's are only averaging about 45 here. So if we take a look at the graph, graphs are used in a portion of the experiment called analysis because it makes sense out of your data chart from here. So we take the data from here and we analyze it by way of a graph. And it allows us to visually see the differences between one group and the experimental group and the control group. A lot of times data tables are a lot more complex than that, and if you're just looking at pages and pages of data tables, it makes no sense until someone goes ahead and puts it into an understandable form like a graph that you see here. We can clearly see plant A is outperforming plant B. The last thing that you do in an experiment is you come up with a conclusion. And I should say the last thing you do in your scientific method. So based on the data, a scientist then determines whether the hypothesis was supported or refuted. So very rarely should we ever say that proved my hypothesis was correct. It only supported it, because you're going to find that as you look at scientific investigations, sometimes it's just not enough. Scientists don't use the word prove because there's no absolutes in science. There's been many times in history where people thought things should have been carved in stone and that's the way it is, and then we found some alternative evidence somewhere else that refuted that initial statement. Some unique facts and limitations about science. Well, in science, every conclusion must assume that the conclusion is only true to the best of our knowledge, and that's about as far as you can go with it. Secondly, while experimentation and observations can provide strong evidence for a conclusion, it's not absolute proof. For example, a man named Charles Darwin and his son noticed the fact that those plants were leaning towards a window. So they did some experiments. They cut the tips off of the plants because they assumed there was a light sensing organ at the tips of the plants that caused them to bend towards the window. So what they did then is they snipped the tips of grasses and plants, and they watched, that was their experiment, they watched to see how the plants would respond. Well, the plants wound up growing straight up. So then they concluded that the plants must have a light sensing organ at their tips, and that's why they grew straight after cutting them off. Well, that wasn't quite the whole picture. If they concluded it and they said, that proves we're right, well, there's some shortcomings there because it only supported their hypothesis. They went ahead and they did more experimentation later, and they found that it might not quite be so, because some alternative explanations came into view. Like, what if by cutting the tip off of a blade of grass, that the wound makes it grow straight? So then what they did then is they re-experimented. They said, all right, so if that's the case, let's not cut the tips off. Let's put some foil over the tips of the grass and see what happens. So they did that, and they wound up taking a look at the results after wrapping the tips in foil. And in this case, it grew straight again. So they kept rehypothesizing and going further and further. They said, okay, there must be some kind of a communication mechanism from the tip down to the center that makes it bend, and it just kept going further and further. So it's not absolute proof, it only supports the hypothesis. Science is subject to change when new evidence is found. So, like I mentioned before, there have been a lot of historical facts that have shown to be incorrect when experimented more thoroughly. For example, in this picture here, you see that when wood is burned, what is left over after you burn wood is a pile of ash. Okay? You also see this crazy word in there called phlogiston. A long time ago, hundreds of years ago, they believed that this chemical called phlogiston was in anything that was able to burn. And after they burned it, the phlogiston went ahead and it flew off into the atmosphere, and what was left over was phlogiston-less matter. So anything that's flammable contains phlogiston. So they went ahead and they burned just about everything, and they came to the conclusion that because after you burn something it's so much lighter, I think we could all agree that ashes are lighter than wood, that must be true. That is, until they went ahead and they started burning some other things. They started burning metals, and they found that when you burn some metals, what you were able to get after was a new substance, but the substance was heavier than the initial metal. And that goes against the whole phlogiston idea, because phlogiston was that as it burns, it goes up into the air, and what's left over is lighter. But this was heavier. So by showing that your results here were something different, and they went and they burned a lot of different metals, they found that indeed when you burn a lot of, for example, the group 2 metals on the periodic table, your result is actually heavier than before you actually burned it. So that goes directly against the idea of phlogiston, and they had to throw the whole idea away because it wasn't true. In fact, what really happened, and we'll use magnesium as an example, when magnesium burned, oxygen from the atmosphere was able to combine with it, and that gave us a new compound called magnesium oxide. And magnesium oxide is heavier than magnesium. Experiments must be repeatable. Okay, if you are the only one that can do your experiment and your experiment is not written up well, it will not garner much respect from the scientific community. So someone should be able to read about your research, perform it themselves, and come up with the same results as you. And last thing I want to say, in terms of just limitations about science, in statistical studies, correlation is not causation. And what that means is, every day when you watch the news, there's some new study about something that's good for you or bad for you. Someone might say, have a study that shows people who take fish oil have a 20% less chance of having heart disease. Okay? If those were the results, that doesn't necessarily mean that the fish oil was the cause of the lower heart disease rate. Because maybe if someone who takes fish oil does a lot of other things that are proactive towards health, it wasn't really the fish oil that did it, but it was the fact that they pay more attention to their own physical well-being than someone else. So correlation is not causation in science. The last few ideas I just want to throw your way are some key terms you hear a lot about in science. For example, theories. Theories are an explanation for a natural event that has been based on a large number of observations or experimentation. Now, unfortunately, a lot of the populace thinks theory is a much lighter term than it actually is. It is based on a large number of observations and experimentation. So that means a lot of work has gone in to come up with a theory. Sometimes you'll hear people say, oh, that climate change, global warming stuff, that's just a theory. Well, yeah, but it's based on a large number of observations that scientists have made and experiments that they have done. So a theory is actually a pretty strong thing. Although rare, theories may be falsifiable, as you just saw with the phlogiston. Every once in a while, someone comes up with some alternative evidence that makes you rethink your theory, and many, many years of burning things, in the case of phlogiston, was all falsified by the burning of certain types of metals. A law can be explained as a natural phenomenon that occurs the same way every time. There's no account of contrary occurrence. So if you think of, for example, Newton's laws from physics, those would be examples of things that occur the same way every time, and we've yet to find anything that goes the other direction with results. And lastly, the term principle is used synonymously with theory. So principle is a pretty strong word as well in science. Just to review, again, different teachers teach the scientific method in different ways. I like to think of it more as a process. There's things that must happen along the way for it to be considered valid science. We talked about observations coming first. We don't even see it on our little picture here. But then from your observations comes identifying the problem, and some people will call this the question, which is absolutely fine. Coming up with a question. Mine was, why do the plants lean towards the window? Then comes the hypothesis. After the hypothesis, we'll perform experiments. During the experiments, we take data and then we organize it and analyze it using graphs. And if we follow our little flow chart here, do experiments and observations support the hypothesis? In some cases, yes. In some cases, no. If the case is yes, you get to celebrate a little bit here, and then you get to write about your conclusions, how your experiment supported the hypothesis that you had, and then you're allowed to communicate those results to other scientists to peer review it. But if you wind up with a no for the support of your hypothesis, that means your hypothesis is rejected. It could be a faulty experiment, but that only paves the way to come up with a new experiment, a new hypothesis, and test something better. Sometimes that will lead you more to the core of the problem, or maybe an offshoot of the problem that you were initially interested in, and you can take your research further. So this is just some basics about the scientific method or process. I hope you understand a little bit better, and I'll see you next time.